Good morning. My name is James Blank. I'm the Dean of the College of Arts and Sciences, and I welcome you to today's symposium. Thank you very much for coming. I know some of you are new to Kent, Ohio. I see many of you around here all the time anyway. I know you're not, but for those of you who are new, welcome to Kent. This is a great, glorious time of the year. Of course, last week it was about 35 degrees, but today's beautiful, and the next few days are supposed to be wonderful. So. Welcome to Kent and Kent State. I encourage you to take advantage of our downtown, which is also, if you haven't seen it prior to this visit, is about half new. About 50% of the downtown when I got here looked about the same until about 2 years ago. A lot of older and tired buildings that would become one student bar after another over 1 or 2 years, but it's all changed, and there's a great connection between the campus and the downtown, which allows you to take advantage of walking there and back. So welcome to Kent. Thank you very much for coming, and encourage you to take advantage of some of the local scenery. I'm a biologist, and I've long had an interest, as some of you know, in biological applications of liquid crystals and biologically compatible materials. I was telling Peter that I made a mistake yesterday when I was looking through the titles and of the talks. I made a mistake of asking one of my colleagues from physics whether all biological materials were soft matter, and I should have known better, because I always get the same answer when I ask a question like that, which is maybe. So I'm really not sure if it is or isn't, but I know some is and maybe some isn't. But I've always had an interest in this area, and I understand the interest in the physical properties at the interface between liquid crystals and nanomaterials, especially when it involves chirality, holds great promise for research, future research. And I'm not sure why chirality matters, but I'll be asking those of you over the next few weeks why, and please don't answer maybe, but tell me why. So I also know a major part of the success of research in this area is going to come from expansion of the type of interdisciplinary research that, in research and education, that's so important for new applications, for developing new applications. And as the home of the Liquid Crystal Institute, we'll be celebrating its 50th anniversary this year, which is amazing that's 50 years already. But more importantly, we'll be looking forward to the next 50 years of research that we look forward to in the future. We all know how important collaborative research is, and so connecting research together from different disciplines, just like the symposium is doing, is going to be really critical for making those sorts of leaps in research happen. So again, welcome. I'm right on time, 15 seconds, so you can begin your symposium. Welcome to Kent, Ohio. Thank you very much for coming, and it's a pleasure to see you.
Okay, so now I get my 5 minutes to say a few things. Again, welcome to Kent State. Welcome to this symposium. The first things we need to take care of is we need to thank those organizations and people that helped fund this. So I'm not going to go into details. You can see most of those are familiar to many of you. A little bit more of housekeeping I want to do. You will find these posters somewhere within the building and right out there in the hallway. If you want to, for example, know more about where to go and where not to get lost, all of those who have a smartphone can use those QR codes there to not only get access to the program and the conference website, you can also find the campus map. So if you get terribly lost, please, before you leave this building, take your smartphone, take a picture of this so that at least you get some help from the mobile device that you have with you. So here you have the website. You will find then the program. And I want to also highlight that if you do eventually go and click on that program link that's up there, you will get every abstract that's been going to be discussed at that meeting, both the talks and the posters as well. So you'll get a PDF file that you can download on your device, iPad, iPod, smartphone, whatever it is. Then I have another little thing, so that's that. Chirality has been an interesting subject for me since many years, and I'm glad to see liquid crystal as well as nanomaterial chirality crazy people in this room. So that's good. I want to maybe kind of put a little bit of something out there. So chirality is a strange subject because we don't really quite understand how all of us became one enantiomer kind of person. Both of the proteins and the sugars in our body are always one type of enantiomer, and we don't quite know how. So there is a nice paper in the Proceedings of the National Academy of Science about the meteorite landing in Australia, on which they actually found enantio enrichment of one of the amino acids. And so that is discussed as one potential opportunity of how, enantio enrichment became part of our life. There's also two very nice papers by leading people in the field that I've highlighted here, and you can email me and I can send you the PDF of these papers, and they kind of try to understand the origin of biological homochirality on this planet. And the nice thing is that one of these papers describes potential mechanisms, and there's about 20 of them discussed in this paper, and the one I like the most is the one on the bottom that's called chiral amnesia. So I'm not quite sure this is a good start for this conference, but so we don't want to get amnesia in the end of it. But at least in this spirit, let's have some fun, and I will spend another 2 minutes introducing our keynote speaker for today, and then we should be up and running. One last thing I want to maybe mention is that I would urge everybody to turn off their cell phones, or at least put it on vibrate. You don't want to have any disruption by that kind of noise coming on. So this gives me the opportunity now to introduce the keynote speaker, Thomas+Burgi. So he is coming to us from Switzerland. He did his PhD at the University of Bern, then did a postdoc at MIT, then went on to do his habilitation at the University of Zurich. So he's moved around quite a bit already at that point. Then became an assistant professor at the University of Neuchâtel, also in Switzerland. Then did the full professorship at the University of Heidelberg, so that's why he's a semi-German fellow of mine. And then went back to get the full professorship at the University of Geneva since 2010. At the time when he was in Neuchâtel, I know we had talked about this briefly, he worked with liquid crystal people. Thoralf Scharf might be a name that tells some people in the audience something. He also worked with Georg Mehl in the UK and with Robert Desgeneux at Neuchâtel. So he has quite a link already to liquid crystals, and hence the choice of having him here as a keynote speaker. I'm very happy to see him here, and I'm looking forward to his keynote presentation. So please join me in welcoming Thomas+Burgi.
Thank you very much, Thorsten, for this kind introduction. Also, thank you very much for setting up this meeting. I think it's very exciting. Normally, if you go to a meeting, you know more or less the people who are there, but here I do not know many people, so that's very exciting. Well, you also put a lot of pressure on my shoulders, saying that I was dealing with liquid crystals. This is, I mean, the liquid crystal part was always, outsourced, so we were more dealing with the nanoparticles. But anyway, let me start here. So chirality is actually nothing very unusual. You can see chiral objects very often in nature. For example, this plant here, that is hops, they are used to make beer. And they grow in a left-handed fashion. They grow up here in a left-handed helix. Or these animals here, they exist in both left and right-handed forms, although not equally abundant. And one form is the mirror image of the other, but you cannot superimpose them on each other, so they are chiral. And finally, this tool here, that's also very important in everyday life. So you can find chirality at different length scales. Obviously, here we have a chiral complex, but you can find chirality also at the nanoscale, and that's what we want to talk about. First, a few words about the interesting chirality, especially in chiral materials. There are several things. I put it up here, two things. One thing is optics. So here we have, for example, liquid crystals, but also metamaterials. That's one big application, let's say, of chiral materials. The other one that's already a huge market, what I call here chiral technology, that concerns the production, separation, and also detection of single enantiomeric forms of molecules. So if you think about pharmaceuticals, agrochemicals, but also flavors and fragrances, this is a huge market. In these markets, you have to very often separate enantiomer or produce selectively one enantiomer. So I would like to start with a couple of examples of chirality, of chiral materials at the nanoscale. So perhaps the most familiar kind of chiral material at the nanoscale is this one here for most of the people here in the audience. So this is a model here for a helical phase of a liquid crystal. So these can be chiral. They have interesting properties. So they're more like in this field here. Nanoparticles can be chiral as well, and we can make nowadays assemblies of nanoparticles which are chiral. One example is shown here. So the Alisatos group, using DNA, tried to assemble like a pyramid, which is chiral. This pyramid contains in the four corners nanoparticles of different size. So of course, such an object is chiral. Okay. So what is the interest in fabricating such objects? This is again in optics. So one interest is metamaterials. A metamaterial, in the narrower sense of the word, is a material which has a negative refractive index. So the refractive index of a material, if it's chiral, can be described by this equation. So this is permeability and permittivity. And if this term here is not too big, and if the material has a large optical activity, so this kappa here, the chirality index is large, you can indeed have a material with a negative refractive index. So this is also a motivation why people try to make chiral nano-objects. Here's another example. Probably we will hear more about this later on in this meeting. So you can make a chiral assembly of nanoparticles if you have rods. You need only 2 rods to make a chiral assembly. So this crossed finger, so you can cross it either like this or like this. So we have the 2 enantiomers, and this has been done here by the Kotov group. And they observed indeed optical activity in plasmonic transitions, which proves that this assembly is chiral. Now, we are probably here because we want to merge like the liquid crystal field and the nanoparticle field. And actually, our chairman is a pioneer in this field. So what his group showed is that if you take a liquid crystal, which shows a nematic phase, and you mix in a chiral nanoparticle, here you can get a helical phase, so a chiral material. This is due to the properties of these chiral nanoparticles. So in my talk, I will mostly focus on this part here of this system, mostly focusing on chiral nanoparticles. Here's a last example. Pure carbon materials can also be chiral. There are chiral fullerenes or carbon nanotubes. They exist in left and right hand-sided form. And what I show here is a Raman spectrum here of the separated enantiomers and the Raman optical activity spectrum. So you can see in this ROA spectrum that for one enantiomer here of the nanotube, the signals are positive, and for the other, the signals are negative. that highlights another important point in the field, namely characterization techniques. Techniques that are sensitive to the chirality. The Raman optical activity is one of these. Okay, let's go back for a while to nature. So as I said, in nature, chiral objects are very often found, like these shells here. However, in nature, and this point was already addressed by Thorsten, the two possible forms are usually not equally abundant. In this case, we have a ratio of 20,000 to 1. It's very high purity, by the way. So if you find one of these, don't throw it away, don't destroy it, just send it to me. I'm looking, since years, I'm looking at every animal, but I've never found one which turns the opposite way. So don't throw it away. Well, this homochirality is also found for the molecules of life, and this has tremendous consequences for chemists, because chemists have to be able to selectively produce one form or the other, or they have to be able to separate the two forms. Now, one particularly interesting case is to do that, to make selectively only one enantiomer, is catalysis. And in particular, heterogeneous catalysis. I'm showing one example here. So in this reaction, a pro-chiral molecule, this alpha ketoester, is transformed to a chiral molecule. So this molecule is not chiral, the product is chiral. This is a hydrogenation reaction, and it runs over a platinum catalyst. If you do this reaction, you will get 50% of this form, 50% of this. However, Orita found many years ago that if you add to the reaction mixture a chiral molecule, this one here, you can direct the reaction to selectively, with very high selectivity, to the R product. So this molecule is able somehow to break the symmetry and direct the reaction to only one product and not the other. By the way, this is an alkaloid here. It has anti-malaria effects, so it's very, very healthy. And you can find it in gin tonic. So if you drink gin tonic, there is a similar molecule inside. So you should drink more gin tonic. So the interesting point here is, in principle, this reaction takes place at the chiral metal surface. Okay. So if chemists think about chirality, they do not normally think about metals and surfaces, but metal surfaces can be chiral as well. And they can be chiral in different ways. For example, if you take a single crystal and you cut it in the right plane, you can get a stepped and kinked surface, which is intrinsically chiral. If you look at this surface, you have these terraces here and the steps, and you have kinks here. So we have 3 atoms here, 2 here, 3, 2. So here, 3, 2, 3, 2. Such a surface is intrinsically chiral, and people have prepared it. Another other type of chirality emerges when we absorb molecules on a symmetric surface, on a non-chiral surface. So one example is here. This is a trivial case. If you just absorb a chiral molecule on an achiral surface, you get a chiral or chirally modified surface. A second case is some sort of supramolecular chirality. So if you put a molecule on a surface which organizes on that surface, and if this overlayer destroys the symmetry of the surface underneath, you get a chiral situation as well. Okay. In this case, the molecule itself does not even have to be chiral. And finally, I put up a third example here. If you absorb a chiral molecule on a surface, it can be that it distorts the surface into a chiral structure. That's what we call a chiral footprint. So these systems have been prepared and studied. So it is known that you can make, in some way, chiral metal surfaces. Our question that we asked some time ago, actually when I was in Neuchâtel, can we now make the nanoscopic analogs to these surfaces chiral as well? So if we have a nanoparticle that is coated with a thiolate, can we make these chiral? So if you think about those two systems, this system here is usually characterized by microscopies, which is very difficult here. But here we have the advantage we can use chiroptical techniques, which are very sensitive to the chirality. So the characterization here is very different. We can also use mass spectrometry to look at composition of this. And if you're lucky, you can grow crystals and look at X-ray structures. Okay. So the question is, can we bestow chirality to metal particles? I will talk a little bit about how we make these particles, briefly, optical properties and circular dichroism of such particles. I will then discuss the structure of a couple of these particles which have been solved. I will talk about the flexibility of these particles. These particles should not be looked at as a rigid object. And I will talk about vibrational circular dichroism, characterization of the particles, and at the end, I will talk about transfer of chirality from the particles to the environment. Something which is important also if we want to combine the two fields, namely liquid crystals and chiral particles. Okay, one brief note on the synthesis. This goes back to a publication by Rust. Basically, what we do is we take a gold salt, it's gold 3, we mix it with a thiol, and this will form a polymer. So the gold is reduced to gold 1, forms a polymer with the thiolate, and this polymer is then reduced using a strong reducing agent. And during this process, we have the formation of gold particles or clusters which are growing, which are passivated then by these thiolates. Okay. So the synthesis is quite robust. Even a physical chemist can do it. The challenging point is then that you do not get only one particle size. You get a distribution. So the challenge is to isolate well-defined particles that we want to study and to purify them. So there are different methods to do this. If you have water-soluble particles, you can use a gel electrophoresis. So you put your particles here in a gel, and you apply an electric field, and the particles will migrate according to their size and their charge. And this is a result of such a separation. You see discrete bands here, which belong to particles with a well-defined composition, so number of gold atoms and number of ligands. This experiment shows you that we can prepare certain sizes of particles, whereas other sizes, so for example here, we cannot prepare. So that in general, if you prepare such a sample, you get certain sizes, but not others. So the particle size distribution is discrete. You can already see by the bare eye that the absorption spectrum is changing if we change the size. So these particles here are the smallest ones. And as we move to bigger ones, there is the absorption onset here, which is moved to the red. These spectra also tell you that the small particles, they are not metallic. So there's a band gap, which then closes as you move to bigger particles. Now for us, interesting point was the following. If we prepare these particles with the two enantiomers of the thiolate, we can get materials which have opposite optical activity. So this is the circular dichroism spectrum. This is, by the way, our work, but the first report on chirality or optical activity in gold cluster was by Rob Wetton, who is here in the audience in the year 2000. So what does that mean? Well, if we look at the absorption of just the ligand, it is down here in the UV. So these bands here, they are located mostly in the metal. So could this mean that the metal is really chiral? That's one possible explanation of this. So where's the origin of this optical activity? There were other explanations, like we have an achiral, a symmetric particle, which is covered by a chiral ligand shell. This induces the optical activity. This is another explanation of this observation. A very important work in the field was the first determination of the structure of such a particle. It was for gold 102 with 44 ligands, done by the Kornberg group a couple of years ago. So this is real structural information. This is the structure of this cluster. And it is covered by this molecule here, which is not chiral. The most important conclusion from this work was the structure of the gold thiolate interface. We all had the structure of the SAM model, self-assembled monolayer model in mind. This was really a surprise here, the surprise is that this structure looks different from the model that was developed for self-assembled monolayers. So what is the structure? So we have a dense metal core, which is not chiral. These are two atoms here of this core, and attached to these two atoms are like these thiolates. So this atom here, the yellow one, these are the sulfur atoms. In between two sulfur atoms, there is here this small atom. This is again a gold atom, which is now retracted from the surface and sandwiched between two sulfur atoms. Okay? So this is the surprising point. For us, interested in chirality, the interesting point is that the structure of this is chiral. And the chirality arises at two levels. The first level, these structures here are arranged on the cluster surface in a chiral fashion. It's not very obvious here, but it's really the case. Second, if we look at the sulfur, it becomes a stereogenic center, like a chiral carbon atom. This is maybe shown here. So we have the sulfur here, which is bound basically to four different substituents. Two different gold atoms here, the organic part here, and then there is the electron lone pair. So this makes this sulfur a stereogenic center. So it can be oriented towards the back here or towards the front. So there are two possibilities. So this is maybe the most recent determination of a crystal structure of such a cluster. It's gold 133 covered with 52 ligands. Again, the ligands are not chiral. What is shown here are just the gold atoms of this cluster and the sulfur atoms. So the organic part was removed. So these small dots here, they are the sulfur atoms. So what you see is that these motifs, these staple motifs, where a surface gold atom is sandwiched between two sulfurs, they are arranged in these ladders here. They form like helical structures. So here's a left helix, here's a right helix. In the crystal, we have both forms, so we have a racemic mixture. They are arranged in this way. So here it's obvious that the surface structure of this cluster is indeed chiral. Here's another example. That's gold 25. Again, we have a dense inner core here, surrounded by such staple motifs. These are now longer. So there are 2 gold atoms in one staple. So this is sulfur, gold, sulfur, gold, sulfur. If you just look at the gold-sulfur framework, so I removed all the ligands, in this case, it's not chiral. Okay? So this is a symmetric structure. However, of course, you can now, instead of an achiral molecule, you can put a chiral one. And if you do that, we can see optical activity in the spectrum, which is shown here, which shows that even if the cluster framework is not chiral, if you put a chiral molecule, here this comfort ion, we can observe optical activity. The optical activity in this case is not very strong, but it can be observed. Finally, I think this is the last structure I show you. This is gold 38. This is our favorite cluster. It's also chiral. These are 2 different views of this cluster. Here with the ligands, this 2 PET ligand, which is not chiral, and here just the gold-sulfur framework. Again, a dense core, which is covered by these staple motifs. In this case, we have long staples here, which are formed in a helical way. So this is like a propeller. This is another view. So this is a side view of the cluster. And in this view, we look along the long axis of the cluster. What you can see clearly here is the left and right hand-sided form of the cluster. Again, we use achiral molecules to prepare it. And in the crystal structure, we have a racemic mixture. So we have 2 forms. So we asked the question, is it possible now to separate these? Because if you want to look at chiroptical properties, you will not observe them if you have a racemic mixture. You have to separate the enantiomers. This turned out to be, it's stuck. This turned out to be easier than we expected. I'm sorry for this. It's not doing anything anymore. Here we go. So this enantiomer separation turned out to be easier as foreseen. We could separate the 2 enantiomers of the chiral cluster using HPLC. So you see these 2 bands here. We collected the 2 bands, and you see optical activity. Now, in this case, the optical activity is relatively strong. So we have 2 interesting cases to compare. We have the gold 25 case, where the cluster framework, so if you just look at the gold atoms and the sulfur atoms, is not chiral. But in this case, we covered the cluster with a chiral molecule. This gives optical activity, but the optical activity is weak. In the second case, the gold 38 case, the cluster framework is chiral. So we have this chiral arrangement of the ligands on the cluster surface, but the molecule on the surface is not chiral. And in this case, we have strong optical activity. So the conclusion is that the optical activity is mostly determined by the chiral arrangement of the ligands on the cluster surface. So we went back to literature, and this, what I show here is a CD spectrum, one of the first that was reported by Rob Wetten. So this is gold-38 covered with glutathione, just after preparation and separation of the different sizes. There was no enantioseparation of this. This cluster was prepared with a chiral ligand. This CD spectrum here is from our cluster, which is covered with an achiral ligand, but where we separated the enantiomers. And this is the CD spectrum of one of the enantiomers. If you compare the two, these spectra look very similar. Okay? So this probably means, I don't know if Rob Whetten has the same opinion, this probably means that more than 10 years ago, Rob Whetten managed to prepare enantiopure or enantio-enriched gold-38 by using a chiral ligand. That's probably what this says. Now, with single enantiomers in our hand, we ask the question, is it possible to racemize these? These two forms have equal energy. So if we start from this form, can we transform it into the other form? Why is this interesting? This is interesting because it would indicate that these structures here on the cluster surface, they can move around, okay, in some way, to go from this structure to the other. So here's the experiment. What we did is we took one enantiomer and we heated it up to different temperatures for 1 hour, so 40 degrees up to 70 degrees. What you see here are the absorption spectra after heating. They look all the same, so the cluster doesn't change. And this is specific for gold-38. So if you would change the cluster, if you would destroy it, the spectrum would change. But no, it doesn't change. We still have gold-38. However, the circular dichroism signal gets weaker as we increase the temperature. So we start with this. After 1 hour at 70 degrees, the CD spectrum is much weaker. So this shows that we have, indeed, racemization. This is also confirmed by HPLC. So this is the initial sample, only one enantiomer. If we heat 15 minutes at 80 degrees, we see the second enantiomer coming up. So the conclusion here is these staple motifs, they can indeed move around on the cluster surface. Once you can follow, once this reaction occurs, this racemization, you can follow it as a function of time. So you can do kinetics. So this is optical activity as a function of time for different temperatures. This is the same data just expressed in enantiomeric excess. So it's obvious that if we increase temperature, the reaction goes faster. And so from this, you can get an activation energy, which turns out to be a little less than 30 kilocalories per mole. So what does that tell us? As I already said, the cluster surface is flexible, so things can move around. But this number here tells us that probably this rearrangement goes on without complete bond breaking. So we do not completely break gold-sulfur bonds. Because a gold-sulfur bond, that's between 40 and 50 kilocalories per mole. Okay. Now, if we want to design clusters with certain properties, an important reaction is ligand exchange. So if we have a cluster covered with one type of ligand, and we bring in a second ligand, this second ligand can attach to the cluster and eject an originally adsorbed ligand. Now, this is a ligand exchange. This is useful if you want to design like clusters with certain properties. For example, you can bring in liquid crystalline like ligands using this reaction. This was done by people like Georg Mehl and others. Now we use a special ligand to do such experiments. Our ligand here is a dithiol, and it is chiral. Okay. So we make exchange using a racemic mixture of these two forms here, so anticlockwise and clockwise cluster, using one enantiomer only of the incoming chiral thiol. We can follow this reaction again using HPLC. So these two peaks here, the first two peaks, they correspond to the initial cluster, which is not ligand exchanged. All the chromatograms are scaled to this peak here. These two peaks here, so the third and the fourth, they correspond to a cluster which has 38 gold atoms, 22 original ligands, and one of the new dithiol ligands. So this composition is confirmed by mass spectrometry. And we have the two forms, so anticlockwise and clockwise. Using this data, we can do kinetics, which is shown here. So this on the left is for the anticlockwise form of the cluster, on the right for the clockwise form of the cluster. The black symbols and the black curve corresponds to the unexchanged cluster. As you see, as a function of time, it just reacts away. What is formed is a cluster which contains one of the new ligands. If you compare these two, it's obvious that one cluster reacts faster than the other, which means that the incoming chiral molecule, it can differentiate between the two forms of the cluster. So there's selectivity in this. You can do this, of course, quantitatively. So if you compare the reaction rates here, this gives you diastereospecificity of about 60%. For this case, we can see this curve here, which goes up, and then later on goes down again. This is due to the fact that when you have this cluster with one ligand exchanged, you can, of course, add a second ligand. Okay. So this species will go again down with time. Okay, so once we had these clusters in hand, so gold 38, 22 PET ligands, and one of the new dithiolate ligands, we repeated this inversion experiments. Remember, I showed the experiments where we inverted the chirality of the gold 38. This is reproduced here again. If you have one dithiolate in there, it doesn't happen at these temperatures. It happens, but at higher temperatures. So only one of these dithiolate ligands on the surface, and the cluster surface gets much more rigid. Here is a summary of such inversion experiments. So it's a Eyring plot. So that's the ln of the rate constants divided by temperature over 1 over temperature. This is the data I already showed you for the gold 38. This is the data for the gold 38, so the two enantiomers, exchanged with one R-BINAS. So there's a clear difference towards higher temperatures. It's also obvious that these two curves here are not the same. So there is, if we have the R-BINAS attached to the two forms of the cluster, this will affect the inversion of the cluster geometry. Another interesting point, we managed to prepare clusters where 2 gold atoms were exchanged by 2 palladium atoms. And this again has an effect on this chiral inversion. It gets more easy now if you have 2 palladium atoms in the cluster. So let's look at another system. Again, ligand exchange, but in this case now, we use a monotile. This one here, the same cluster. So if you think about this system, the cluster can exchange only basically at 4 symmetry equivalent positions. So this position here, that's the same as this one. This position here, and this here. All others are equivalent. For example, this one here, that's the same as this. So there are only 4 possibilities for the first ligand exchange, where the ligand can go. So if you do this experiment, that's what you see. So here are mass spectra. This is before the reaction, also this is the mass of the gold-38. At short time after ligand exchange, we get an additional peak here, which corresponds to this mass. So 38 gold atoms, only 23 ligands, original ligands now, and 1 of the new ligands. So we have replaced 1 of the original by 1 new ligand. Okay, that's what this means. If we look at HPLC of this sample here, we see the peaks for the 2 enantiomers of the cluster unexchanged, and we see here small peaks. Okay, and we see a couple of them. Now the interpretation here is that this corresponds to species with exactly 1 ligand exchanged, but at different positions. So we're talking about isomers here. So for example, a ligand exchanged here or here, it's not the same, and we can separate these using the chromatography. So we repeated the experiment with only 1 enantiomer of the cluster. Again, we get several small peaks. And I told then the postdoc, and at this point she was going mad, she should now isolate this species here. This is very tedious work, but it can be done. So she collected this species, and that's the re-injected sample. So you get only 1 peak. What does this mean? You can isolate species with exactly 1 ligand exchanged at 1 specific position. Now, interestingly, if you now take this and heat it up to different temperatures, for example, here 80 degrees for 30 minutes, the other peaks reappear again. Okay? So what does that mean? This means that if, for example, you exchange at this position, this ligand can move around on the surface to different positions which are not the same by symmetry. So this again shows you that this cluster surface, it's nothing which is rigid. Things can move around at slightly elevated temperatures. Okay, I'm almost done, but I would like to discuss a little bit with you one interesting technique that we apply to these clusters, which is vibrational circular dichroism. So basically, I've already shown you some circular dichroism spectra. These probed electronic transitions in these materials. But we can do the same in the infrared. And then we are probing like the ligand shell. Here we're looking at electronic transitions. here at vibrational transitions. So circular dichroism is the differential absorption of left and right circular polarized light. This is actually a nice technique because you can get information about the absolute configuration. So by this technique, you can determine if a molecule is left or right. More importantly, even for this, you can learn something about the conformation of a molecule because the VCD spectra are very sensitive to conformation. Here's an example. So here we prepared particles covered with this chiral tile. These are infrared spectra. They look the same. These are VCD spectra. They have opposite sign. Another example, so we prepared particles covered with this dithiolate. This is just to show you the comparison between calculated spectra and experimental spectra. You have to do calculations. It's by the comparison between experiment and calculation that you get the structural information. So if you just compare calculation and experiment for just the molecule, you can see almost a perfect match. It's beautiful even for a theoretician, right? Okay. If you put the molecule on the cluster, the spectrum changes. But again, if you just look at such a primitive model here, we can fairly well reproduce the spectrum. But this gives us confidence that this technique can give us information about the structure of molecules, of chiral molecules, which are adsorbed on the clusters. Okay, so last point here. We looked in more detail into the infrared spectra of our favorite cluster, so the gold 38, which is covered by this thiolate, which is not chiral. So what I show you here are infrared spectra measured of just this molecule and of the cluster. Measured in black here and calculations in red and blue. Now, this molecule can adopt different conformations. The molecule is obviously not chiral, but it can adopt a chiral conformation. I would call this a transiently chiral species. I call it a gauche here. In contrast to the anti-conformation, which has a plane of symmetry and which gives a different spectrum in comparison to the gauche. The spectrum differs in this band here, which is a CH2 vibration, and if you turn around this bond here, this will affect the position of this band. So if you now compare the calculations here with the experiment, we can see, okay, if you just take this liquid, stinky liquid, you get both forms in the sample. Okay. Now, if you look at the cluster, the same thing. So this is the calculation. Sorry, this is the experiment. These are the calculations for a model, which I do not describe here, containing just gauche conformation of the molecule and anti. And it's evident here that we have in our sample a high fraction of gauche conformers. Okay. These are transiently chiral. Okay. Now, in this sample here, we have, of course, 50% of one form and 50% of the other. But this is not true anymore if we adsorb the molecule on the cluster. This is evidenced by vibrational circular dichroism. So this is the VCD spectrum of the two enantiomers of the cluster with this molecule adsorbed. And the molecule, once again, is not chiral in principle. But still we see VCD. And this means that the chiral cluster can transfer its information, so the chiral information, to the adsorbed molecule. We can even say that so which handedness of the cluster gives rise to which handedness of the adsorbed molecule. Okay? And I think this is an important finding also for your field. This shows that the chiral properties of the cluster can be transferred to its environment. So this is good news, in principle. So with this, I think I will conclude. I've shown you that chirality can be bestowed onto metal particles and clusters. These days we can prepare truly monodisperse clusters, so where we exactly know the composition, number of gold atoms and ligands. We can separate enantiomers. This has been done for several clusters by now. In my eye, an important point is that the cluster surface, it's not rigid. Things can move around. And actually, when we were working in the liquid crystal field, so when we were trying to attach mesogenes onto the gold particles, these were not extremely well defined at that point in time. We sometimes observed that we needed to heat up the sample before it showed a liquid crystalline phase. And having this now in mind, that the cluster surface is not rigid, this probably means that the randomly attached mesogenes, they had to first go to the right positions to form the liquid crystalline phases. So this is a good point that the things are not rigid, but for certain applications it can also be a challenge, let's say. We've also shown that you can, by introducing a bidentate ligand, you can work on the rigidity of this cluster shell. Ligands can migrate on the surface, and I think that's a very good news as well. Chiral clusters are able to transfer their chirality to the surrounding. So I think with this, I would like to thank the financial support here. Most of the work was done by two former PhD students, so Cyril Gauthier and Stefan Knoppe, and some of the separation work was done by Dr. Igor Dolamic. So with this, I would like to thank you once again for inviting me. I wish a happy birthday to the Liquid Crystal Institute, and thank you very much for your attention.
Okay, we have plenty of time for hopefully lively discussion. And you got first.
You've attached glutathione, a tripeptide, to your sulfur clusters. Has anybody tried larger proteins, like the coagulation proteins? And a lot of proteins have sulfhydryl groups on their surface.
Yes, this has been tried like for the bigger particles, like the plasmonic particles. Not that I know for the smaller cluster that I was talking about.
I see
It's
a lot
maybe
of
something-
potential. I see a lot of potential for this sort of thing for biologists.
Yes. I mean, you have to keep in mind the sizes. If you look at these clusters here, say the core is on the order of 1 nanometer. If you take the shell, it's 2 nanometers, something like this. So your protein is the same size or bigger. In many cases.
Oh, yeah.
Thank you very much. It was an excellent talk, and I enjoyed it very much. So, there are a couple of questions which kind of generated along the way. One is, I like the point about the mobility of the ligands on the surface and the replacement of the ligands eyes into it, and how to separate one position against the other position. My thinking about it is that the decrease of the temperature should force basically the equilibrium into one side, into one type of the orientation. Is that your thinking as well, or it's not enough?
Yes, of course. So this is, you're talking about the thermodynamic stabilities of the different positions, you know.
And kinetics.
And kinetics. Too. So what you observe, if I go back, it's maybe best seen here. So this is the sample starting from just one enantiomer of the cluster and doing the exchange. So we see three bands. There might be more underneath here, right? So this is after ligand exchange. What is obvious is that this band number 2, which we collected, is less intense than the other two. So this must mean that the exchange, so this is now the kinetics, the exchange of the ligand is not equally likely at the different positions. This has been shown also for the gold-25. The gold-25 has only basically 2 different kind of positions, and it has been shown by NMR that the exchange at the 2 positions is not equally likely. Okay. Now this represents the kinetics of the exchange for the incoming molecule. This does not have to be the thermodynamically most likely position. So it can be, when you now heat this up, that it will, the different probabilities will change, the different abundances. We have no clear indication, let's say, from these experiments, because we didn't have enough sample here. But I think I would agree with you. This is probably going to happen, so that you can move things around towards the more thermodynamically favorable position. That's, by the way, what I think happens also with these particles that are modified with these liquid crystals. So if you just do the exchange, they are probably in some way randomly distributed. If you heat them up and you allow the mobility, they will go to a thermodynamically favorable arrangement, which is, by the way, then driven by the liquid crystalline phase. Yes. So I think this mobility is very important.
Who would ask another question, Thomas?
Cool.
It's in respect to the last part, about how the chirality of the cluster is influenced, influencing the chirality of the attached staple. Yeah. I need to say that after that I want to find some means and to get into my lab vibrational circular dichroism. Question is, if it considering this should have some implication for catalytic reactions at the gold surface. Do you see any kind of obvious extension of that structure in catalysis? And that would possibly connect to the homochirality that we started with. So a little bit further view, if you don't mind.
Of course, it is known that gold clusters or small particles are catalytically active. For certain reactions, gold is not a good catalyst. If you talk about bulk gold, for example, CO oxidation, bulk gold is not a catalyst. But if you make nano-sized particles, it becomes a catalyst. Okay. And so it's obvious to the idea, so to extend now this concept towards catalysis, trying to catalyze, reactions using these particles. This has been done by, for example, the Chin group and others. And then, even further, you could think, okay, if you can have a chiral particle, why not try enantioselective reactions? I know that this has been tried by at least 2 groups, but up to now it didn't work. Okay. Yes.
Do you have any thoughts why it didn't work?
Well,
Because
my thought about this is for the reactions that were tried, during the catalytic reaction, you do not have necessarily this structure anymore. Can be, for example, things that were tried with oxidation, and I believe that at least part of the ligands is probably removed during these reactions. But I know that more than 1 group or more than 2 groups in the world are trying this.
About racemization of your clusters, how do you envision it? Is it a one-step racemization or multi-step through some kind of quasi-equilibrium states? How it happens?
Yeah. Okay. This cluster here, as I said, is chiral because it has this fan here, which in this case is turning right. There is the same on the opposite side of the cluster. Okay. Both are turning in the same direction. So right here on top, right at the bottom. Now it's obvious that you have to go from here to here, you have to turn both these. Yeah? I would suspect that this happens in 2 steps. Because if you look at, maybe I show this here. So you have this turn here, which is on this side, and we have the same handedness on the other side. Now it can be that at some point one side turns, but not yet the other, and this turns then in a second step. Right? So you would have an intermediate which turns, for example, left here and on the other side right. This is not chiral anymore, this is a mesoform. So I imagine this goes in 2 steps, but I don't know. Okay? And also what we do not know, of course, is how it really happens. So we proposed basically 2 mechanisms. One is that basically these units here can, for example, this sulfur atom can slide, for example, along this bond, so here, and in a concerted way the second and the third.
So the top fan changes also not instantaneously, but step by step.
There has to be also at least 2 steps. The second mechanism could involve, like, mixing of the of these thiolate structures. If you have a kind of SN2 reaction, so where, for example, a bond is formed between this edge here and this one, and the same again for the 2 other sides. This we don't know.
And the energy corresponds to some kind of largest barrier in your multi-step.
I have one last question. So you talked about the transfer of chirality from the cluster itself to the surrounding ligands. You have to speculate how far would that influence reach?
It's a difficult question, no? I mean, anyway, the question is, how does this work at all? So, my feeling is there's an influence of crowding here on the surface. So the fact that these ligands are arranged in a chiral fashion on the surface makes some sort of like chiral pockets where each of the ligand is sitting in, and this chiral pocket makes the inequality between the two enantiomeric forms. So this would mean that this effect that I was just describing is just in the area where we have the crowding. But of course, if you have now here like a chiral structure, this can further be promoted farther away from the cluster.
It would be good for me.
Yeah. No promise, but yeah.
Question maybe?
I have a question about the gold-38 clusters. The gold-38 clusters are chiral, right? Have you tested chiral ligands with the chiral cluster to see if maybe there's a greater optical effect from pairing them than there is with just a separate chiral cluster and a chiral ligand?
No, we have not done these experiments. I would expect that the optical activity is really, dictated by the arrangement of the cluster or of the thiolates on the cluster, rather than the optical activity or the chirality of the ligand itself. And I'm going back here to this comparison. One point is this. So this was this is gold-38, which contains a chiral molecule in its ligand shell. It's glutathione. It's a tripeptide. And this is our gold-38 with achiral molecules. And the optical activity, or let's say the anisotropy factors, they are, let's say, similar. So I would guess that it is really the arrangement which dictates the strength of the optical activity rather than the chirality of the molecule.
Okay, I think in the interest of refueling with coffee, we can stop at that point here, and please join me in thanking Thomas for this interesting talk.